Hello everyone, my name is Florin Teleanu and I will take you through some of our recent work at NYU regarding modeling intermolecular polarization transfer in ionic liquids. First, let's start by looking at our system. We've chosen imidazolium-based ionic liquids which produce very clean proton spectra, making assignment straightforward. Then, we ran Hosey experiments with this pulse sequence such that we transfer polarization from fluorine nuclei on the anion to the protons residing on the organic cation. Following, we derived the characteristic heteronuclear cross-relaxation rates for the two samples, one with tetrafluoroborate and the other one with hexafluorophosphate as the counterion. You already see the different temperature trends of the transfer for the two samples, and that's what we were interested in explaining. To do that, we ran molecular dynamic simulations of pure ionic liquids to understand what's going on as our spins tumble in solution, and more importantly, what are the mechanisms impacting intermolecular Overhauser effect and its temperature dependence. As you see here, the radial distribution function, which describes the probability of having two atoms at a certain distance, does not change significantly with temperature, while the mean square displacement of the cations and implicitly their diffusion rates are steadily increasing. This implies that even though the average spatial proximity of proton and fluorine atoms is rather constant, it's the time modulation of the dipolar interaction that changes as ions diffuse faster with increasing temperature. As we already know, the dipolar interaction is dictated by the relative orientation of the vector connecting the two nuclei with respect to the main magnetic field, and in solution, its modulation due to molecular tumbling leads to relaxation. We used MD simulations to keep track of these changes by building the time-dependent dipolar tensor and analyze its autocorrelation function. You see that higher temperature leads to a faster loss of correlation between consecutive frames, meaning that the correlation time of the intermolecular interaction decreases. Having all this, we can build a spectral density characterizing the transfer and predict the cross-relaxation rates at different temperatures. Curiously, we noticed that by scaling the distance-dependent cross-relaxation rate with the probability of nuclei being at that distance, the way different shells contribute to the overall polarization transfer changes with temperature. More explicitly, there are tumbling regimes where shells' contributions are additive, but they can also interfere destructively with closer shells showing a negative cross-relaxation rate, which is compensated by the positive contribution of the more distant ones. On the right, you see the integral of the left plot showing how these contributions converge and even change sign when accounting for more distant spins. The same pattern is replicated when we computed the cross-relaxation rate from MD simulations by including more and more shells in our model. This approach allowed us to have very good match between experiments and predicted values, confirming our computational workflow. And in the end, I would like to thank you for scrolling up to this presentation and encourage you to further read our paper published this year.